Welcome to this explainer. Okay, let's dive right into this, because I am just absolutely thrilled to explore how OpenAI took a deeply traditional piece of technology and scaled it literally to the moon. We're looking at PostgreSQL. Now, this is a relational database originally created by university scientists decades ago. It's incredibly reliable, for sure, but historically, it was never really designed to be a hyperscale, globally distributed behemoth. Yet somehow, OpenAI actually managed to push it to handle absolutely mind-boggling global traffic. So I want you to just think about that for a second. How exactly would you architect a system for a massive global audience hitting it with millions of queries per second? A heavy read and write workload like this means the database is constantly being hammered with users asking for new information while simultaneously saving millions of new chat logs every single second. With zero room for error, it kind of sounds like an impossible task that would require something incredibly exotic. 800 million users. Just take a moment to let the sheer scale and weight of that number sink in. That's the ChatGPT user base relying on this infrastructure. Normally, an operation of this magnitude would require a sprawling, globally distributed, custom-built web of highly specialized databases just to keep the lights on and prevent the servers from immediately melting down. But here's the absolute incredible twist. This massive scale is actually powered by a single primary Azure PostgreSQL server. I mean, it's the ultimate underdog story of system design. Usually, when you're building for this size, you'd shard your data, meaning you slice it up and distribute it across hundreds of different primary servers. But OpenAI, they kept it all pointing to one single source of truth, one primary writer doing all the heavy lifting for the most popular AI application on Earth. So let's look at Section 1, when the system cracked, the breaking point of scale. To put the stakes into perspective here, during the viral launch of ChatGPT Image Gen, 100 million new users signed up in a single week, right? 100 million. What actually happens to a server when a tsunami of traffic like that hits? Well, it doesn't just quietly slow down. Memory maxes out, request queues fill up, the CPU overheats, and eventually the fundamental architecture just breaks. This massive wave created a 10x spike in write traffic almost overnight. And this huge surge, it actually resulted in their only major Sevi 0 crash in an entire year. Now, if you're a beginner engineer, a Sevi 0 is basically a nightmare scenario. It means a total system failure, nobody could use the app, alarms were blaring across the engineering floor, and the database was just completely crushed under the weight of the traffic. So why did it break? Well, it comes down to a database mechanism called MVCC, or Multi-Version Concurrency Control. In simple English, under heavy writes, MVCC forces Postgres to copy whole rows of data, even if you're just making a tiny update to a single field. This creates massive write amplification. It's exactly like having to photocopy an entire book just to fix a single typo on one page. Now imagine 100 million people all forcing the database to photocopy books at the exact same time. The CPU literally just runs out of computing power. Okay, let's dive into Section 2, protecting the single writer, engineering the defense. So how do you protect that single primary database from melting down under all that pressure? Their core strategy became rule number 1, offload the reads. They moved as much read traffic as humanly possible away from the primary writer to nearly 50 read replicas spread globally. Think about how much relief this provides. For an AI app, 99% of what users do is read. They're asking ChatGPT to retrieve and generate data. So shifting all of that away from the primary is a massive lifeline. But you also have to optimize the traffic itself. They discovered that one bad query, like say a massive operation joining 12 different tables together, could consume all the CPU and degrade the whole service. So they moved complex logic out of the database and up to the application layer. They set strict timeouts so idle queries don't clog the pipes, and critically, they physically separated workloads to avoid what's called a noisy neighbor. By routing high and low priority requests to completely different instances, a heavy background task can never steal CPU from a user actively waiting for a chat response. Moving on to Section 3, smart connections and caching, working smarter, not harder. So Azure Postgres limits each instance to 5,000 connections. With millions of queries a second, that is a huge bottleneck. To prevent the system from getting overwhelmed, they used connection pooling via a proxy called PG Bouncer. Think of PG Bouncer kind of like a bouncer at a really busy exclusive club. Instead of letting 50,000 people rush the door at once and trample each other, the bouncer manages a neat line, letting people in only when there's space, and efficiently reusing the active spots inside. And this brilliantly illustrates the impact. By introducing that proxy layer, the connection setup time was slashed from 50 milliseconds down to just 5 milliseconds. That's a 90% reduction. Dropping from 50 milliseconds to 5 might sound small on paper, but when you multiply that by millions of queries, it literally saves hours of computing time every single second, freeing up massive amounts of resources instantly. They also implemented this incredibly clever thing called cache locking. Imagine 10,000 people ask ChatGPT for the exact same popular fact at the exact same millisecond, and it's not in the fast cache. Instead of all 10,000 requests hammering the database in what's called a retry storm, which would instantly crash it, cache locking means only one request gets the lock to go fetch the data. The other 9,999 just wait for a fraction of a second until that first request populates the cache for everyone. It completely saves the database from an avalanche of redundant reads. Which brings us to Section 4, the results and future. Solid engineering beats hype. I mean, these numbers are simply jaw-dropping. By applying solid fundamentals, they achieved 99.999% availability, what engineers call 5 nines. They're running nearly 50 global read replicas. And their P99 client latency is still sitting at a blazing fast low double-digit milliseconds. That means even for the unluckiest 1% of users on the worst possible network connection, the database responds basically in the blink of an eye. But, they aren't stopping there. To scale beyond 100 replicas in the future, they're testing cascading replication. This is where intermediate replicas relay the data to other downstream replicas, sort of like a telephone tree. And this is necessary because of basic physics. There's only so much data a single network cable can push out to 100 different servers at once. Cascading ensures the primary's network bandwidth doesn't get exhausted. Seeing how a traditional system like PostgreSQL can be pushed to handle 800 million users leaves us with a really fascinating question. Will traditional, well-engineered databases continue to outlast the hype of flashy new tech? It really just goes to show that mastering the absolute fundamentals of system design can unlock unimaginable scale. I really hope this explainer sparked your curiosity to dig deeper into the incredible world of engineering. Keep learning, and I'll catch you in the next one.